Hello everyone. In this session, we are going to talk about PyTorch, one of the most widely used deep learning frameworks. PyTorch is an open source framework. What makes it specifically attractive to researchers, developers, and to everyone is that it's Pythonic, user-friendly, meaning it integrates seamlessly with Python and feels very intuitive to use. It's also flexible, giving you the freedom to build, modify, and debug your models easily. And unlike static frameworks, PyTorch uses dynamic computation graphs, which is great for models where structure may vary during runtime. And at the core of PyTorch are something called tensors, which are basically multi-dimensional arrays, just like NumPy arrays but with GPU acceleration. For example, a vector in NumPy is similar to a 1D tensor in PyTorch. A matrix is a 2D tensor, and it can extend to higher dimensions for more complex data. Also, PyTorch has a huge community behind it. It's trusted by top AI labs and used in both cutting-edge research and production environments. PyTorch scales with your needs, whether you are just experimenting with a small idea or building a full-fledged production system. PyTorch can support you. It's designed to be fast for prototyping and powerful enough for deploying large production-level models. Let's look at the core modules that PyTorch provides. Firstly, you can control where your tensors are allocated on a CPU, GPU, which is important for performance. It handles automatic differentiation, so no need to manually derive gradients. It gives you access to a wide range of optimization algorithms like SGD, ADAM, and more. You can even use Tensor board to visualize the training progress, model graphs, and hyperparameter tuning. Now, let's talk about TorchNN, which is a module for building neural networks. You will find everything here, from convolution layers, activation functions, to loss functions, and more. And I want to quickly show you this valuable resource, which is a PyTorch official website. So in the website, you can find learning materials, like if you go here, for example, learn the basic, you can see you can learn how to do data augmentation, feature extraction for audio, for images, for anything. You will find here the community hub, so you can connect with people or learn from them, discuss with each other in Slack or other platforms. And here is the documentation. If you go to the documentation section, you can find the APIs provided here. Like, let's open TorchNN that we just discussed. So you can see, for example, loss functions. You can see a variety of different loss functions implemented here. So let's open, for example, the cross entropy one. You can find the math behind it. You can find the source code above here. So this website is an excellent reference when you are going to implement or customize models. So bookmark it and refer to it often. One of the biggest strengths in PyTorch is its rich ecosystem. Let me highlight some popular libraries built around PyTorch. TorchVision, which is built for computer vision tasks, including popular datasets, pre-trained models that you can use directly for solving your problem. Other libraries can be found for object detection or segmentation, for fast and flexible image augmentation. For NLP domain, you can find TorchText for natural language processing, audio for audio and signal processing, Torchaudio for working with geospatial data, TorchRec for recommendation systems. And PyTorch Geometric is very powerful for graph neural networks. These tools come with popular datasets and pre-trained models, making it easier to benchmark, prototype, or apply transfer learning to your custom problems. To wrap up, PyTorch lets you focus on solving the actual problem rather than worrying about low-level implementation details. It's very powerful, intuitive, and backed by a vibrant community and extensive resources. Make sure to visit the official website, explore the documentation, tutorials, and examples. It's one of the best ways to deepen your understanding and to get inspired. And thank you.
In this section of the recitation, we'll be walking through some sample problems involving PyTorch and showing you how you can use it and make your own very simple neural network and train it on publicly available data. Before we move into the practice problems, we'd like to cover some prerequisites for running the notebook. So far, we expect that you have seen recitations 0.1, 0.2, and 0.3, which cover the fundamentals of Python, NumPy, notebooks, and Conda environments, which are all very important in terms of understanding just the general framework that you need for running this kind of code. We're also expecting that you'll have some very basic math or matrix algebra, maybe from an undergrad course. This is not as important, but it's helpful in terms of visualizing what exactly arrays are and linking them to matrices. And then further, when we start talking about tensors, that'll also begin to make more sense if you've dealt with linear algebra before. So diving right into the notebook, you can see that this is what the notebook looks like. In addition to the prerequisite recitations, as you've seen, we also have a README in the beginning of the notebook that has some very helpful links, for example, to NumPy. And you can see, for example, on the NumPy website, they have a try NumPy feature, which you might have already seen before. And this will walk you through some sample problems that will get you a general understanding of arrays, especially multi-dimensional arrays, which we'll be using a lot. Another helpful link is the PyTorch link itself. So PyTorch has a great website that talks about how exactly you can install it, depending on what your platform is. So for example, if you're using Ubuntu, as I am, Windows, Mac, etc., they also have some very helpful documentation for all the different functions that you'll be using. And they also have projects that people have made, and you can see tutorials as well, just in terms of, if you want to learn the basics, if you want to get understanding on even more complex topics like processing images and videos, reinforcement learning, etc. And so if you have some extra time over the summer and you want to read into it, I think that this is a great resource to dive in to the concepts right before the class starts. Yeah, in addition to the README, the notebook is divided into 4 major sections. So the first 3 sections deal with just simple functions related to PyTorch that you'll be using a lot, and that will be very helpful for you as you start building and training your networks. And the fourth section deals with actually building a network and training it and seeing what the accuracy is, which we'll walk you through in a little bit. So starting with the very first section, we're dealing with interconversions between NumPy arrays and PyTorch tensors. So just as a brief background, there will be other material on this, but tensors are essentially you can think of tensors as the equivalent of NumPy arrays for PyTorch. The advantage that tensors give you is that they allow you to very easily parallelize a lot of processes. For example, multiplication, differentiation, the things that you do for forward and backward propagation. Tensors allow you to parallelize that and distribute it over your computational resource. For example, if you're using a GPU, very easily. And so in our class, in general for machine and deep learning, you will be seeing a lot of tensor manipulation, and we use tensors really to represent all facets of the model, from the model weights to the gradients to the input and output data, etc. So really, they're very helpful in terms of just data representation in a very efficient way. And so in the first section, we'll be dealing again with interconversion. So you see that there are these 2 functions that deal with converting between NumPy arrays to tensors and vice versa. And you can see that really some of the answers can be very simple. In section 2, we'll be dealing with, okay, so now you have this data represented in terms of an array. What are some manipulations that I can do off that array, or some mathematical operations that I can perform on that array? So some examples of the math that we can do is an outer product. So that's if you want to multiply 2 of your tensors together. Sum product, when you're training, you might see an activation function, which is essentially like a mask that talks about whether an array is enough to excite your neural network or not. And so you can also implement the ReLU activation function, which is a very common activation function, very frequently used in deep learning, and prime ReLU, which is the derivative of the ReLU function. In section 3, we'll be dealing with more of the logistical things related to tensors, so tensor manipulations, just general operations that you can perform on tensors. So, for example, if I'm dealing with a multi-dimensional tensor array, that let's say I have a 3D array that deals with RGB images, as we'll see soon. Let's say I want to flatten my data because it's faster to process that way, so I can do that. We can stack multiple arrays together. Oops. Um, yeah, we can stack multiple arrays together, we can do padding, and really all these different processes that we're talking about. And this code walks you through how you can implement them, and then you can test it. So right now it's not implemented, but we highly recommend that you walk through this code and implement these different features, because it's very, very helpful just in terms of familiarizing yourself with general tensors and general tensor manipulation, which you'll be seeing a lot in your homework part twos, especially. And then finally, in section 4, we're going to build our own neural network and train it on a publicly available data. So the specific data set that we're dealing with is called the MNIST database, which is essentially just a collection of images of handwritten digits, and it's very frequently used as a benchmark for vision-based models. So you can see that because I'm dealing with images, I'm installing the TorchVision submodule within PyTorch. And you can see that the requirement is already satisfied because in this notebook, I have already run it before and it has that specific um, library already installed. Next, I'm going to import my PyTorch. So you can see that I have said um, the specific statement that you will be seeing very frequently is import torch.nn as nn. So the nn is the neural network module within PyTorch that allows you to create all the different architectures that we talk about throughout the class. Really, this is the basic building block that we need. And so I'm going to import all of these libraries. And then I'm going to cast my model onto, or I'm going to specify a device for which I can cast my model. What this really means is that on every computer, I have the option to either do my computation using my computer's CPU or using the GPU, which allows better parallelizability. Or if I'm connected remotely, for example, in this case, you can see I'm in Google Colab. I can connect to a remote GPU and use that for my computation as well. And there will be another recitation in the future that deals with how exactly you can do this and the fundamentals of Google Colab. For now, I'm just going to run this on my device CPU. So you can see that I'm running, because I'm just using a simple CPU, the device type is CPU, which means that it's going to use my computer CPU for doing any forward and backward propagation or any computation that it needs. Now I can move on to the actually exciting part of building my neural network, which I'll then train on this data set. So you can see here that in the init function, I have the architecture of my neural network defined, which in this case is a very simple three-layered neural network. All layers are fully connected, and I'm essentially creating kind of an inverse pyramid where I take in the input size that I have, and I'm essentially just stepping it down so that I can select the features that truly matter in terms of improving my classification. One other function that I'll define in my class is the forward function, which is going to be used to actually train the network. And then finally, I'll create my neural network and then I will cast it to my device. And what this line is doing is it's telling the program to use my specified computational resource to do any training or inference. So in this case, for example, as you remember, I used my CPU as my device. So I'm essentially telling it to use that as the computational resource when it is training the network and to cast, essentially just store that network on that device. Now, next, I'm going to load in my data set. So again, we're dealing with the MNIST data set, which is essentially pictures, which are represented in terms of tensor arrays of like pixel values. Along with loading the data set itself, I'm also going to transform it to essentially mean shift my data or normalize it, which means that if I have a data point that is for some reason or like a cluster of data points that are for some reason way off the mean, it'll essentially just batch them and then mean them together so that I don't have to worry about variations between different data points. And so I am going to run this, which should hopefully load the dataset. And yeah, you'll see those bars if you run it for the first time. Since I've run this before, it already assumes that I have the dataset. Next, I'm going to define the loss function and the optimizer. Again, these I am defining on the basis of what my data set itself is. So, depending on what kind of data you're dealing with, whether you're doing classification or whether you're doing mean squared error loss, where I want to predict an exact value, you have different loss values that you can use. Here, I'll be using cross entropy loss. And then for my optimizer, I'll be using stochastic gradient descent. And then finally, I can begin my actual training. So you can see here that I'm only training it for 5 epochs just to show you what it looks like. And then for each epoch, I am essentially going to put in the inputs and the labels. So the input is the actual data, and then the label is the classification that I want my model to learn. And then my loss is going to be updated based on what the model predicts. And the optimizer and the loss will both be stepped in each epoch. And you can see it's a little bit slow because I'm running it on my CPU. And you can see that it takes maybe roughly like 10 seconds per epoch. And I'll stop it in the middle now just so that we can move on. But feel free to run it for more and more epochs to see what that training improvement looks like. And then finally, in the last section, we have a place where we're actually checking what the accuracy is. So if I run this, I will see a little print statement in the end that says that the accuracy of my network on 10,000 test images is 96.86%. That's very impressive. I mean, I only trained it for 2 epochs. That means that, what we're seeing here, for example, is that if you have a lot of data, even with a simple neural network, you can create a very powerful prediction machine. So hopefully this section helped you understand the general pipeline of building, training, and testing your own simple neural network. And of course, in the class, we'll be really focusing the heaviest on this section where we're building the neural network and testing out different architectures for the neural network itself, and then also different types of neural networks and deep learning networks. And we'll be playing around with different types of data, different types of loss functions, optimizers, and different ablations for training the network itself. Hopefully, this notebook and the rest of the content is helpful in terms of understanding the fundamentals of PyTorch and the basic information that you need to start building and training your own networks. And we hope to see you in the next recitation.